This is the first in a series of videos on Chapter 8, which discusses relations, properties of relations, and we're going to finish up with something a little bit outside of this set, which is looking at the pigeonhole principle. Section 8.1 begins by looking at some relations that are on sets. I'm going to do some problems that are slightly different in some cases from your text, just so you have something different to look at. Here I have a relation on a set where I've taken the real numbers across the real numbers, so I'm working with the number line across the number line, and we have the Cartesian coordinate system. And I'm going to say x is going to be by, means x is greater than or equal to y. So b you can think of as being bigger or equal to. So, what does this thing look like? Well, if we wanted to look at the set of all the ones where x was equal to y, it would be this diagonal line here. So all the ones where x is bigger are going to be to the right, or bottom if you rather, of that line. Now, using this notation, we can say, does or is 4b 3? Well, looking at the relationship here, 4 is greater than or equal to 3, so the answer is yes. And if you look at this, 1, 2, 3, 4, 1, 2, 3, puts this clearly in the shaded region. How about 3b3? In other words, is 3 greater than or equal to 3? And the answer again is yes, because it has the equals property. It's one of the points that's directly on this line. Is 2b3? Is 2 greater than or equal to 3? The answer to that one is no. So this is the kind of notation we're using with these sets. Here's another one that's kind of interesting, and we're going to see this one pop up in some later experiences as we go through the chapter. What I'm looking at is something called congruence mod 2 as a relation. We're going to define the relation E, and I think it might become apparent why I used the letter E for this one, that goes from the integers to the integers. And we're going to say that a pair of integers then is going to be in z cross z, and m is going to en, means that m minus n is even. So now I've got a bunch of questions about this, starting with does 2e4? Well, if you look at the second part of this, if we were to take 2 minus 4, that's going to give us what? Negative 2, and that is even, so it's a yes. Does 2e3? Well, if you take a look at 2 minus 3, we get negative 1, which is not even, so that's a no. How about 2e 2? Well, 2 minus 2 is 0. That's an even number, so that's yes. Does 2e negative 2? 2 minus a negative 2 is going to be 4, which is even, so that's a yes. Does 1e 2? Well, is 1 minus 2, that one's going to give us negative 1, so that one's a no. Does 1e3? If I take 1 and subtract 3, I get negative 2, which is even, so that's a yes. Does 1e negative 1? 1 minus a negative 1 is 2, so those two do each other. Well, let's look at this in a little different way now. What numbers are going to e 2? Well, certainly we've seen 2 is going to E2, 4 is going to E2, 6 is going to E2, and certainly going up with these multiples of 2 is going to work. We've also seen 0 is going to E2, negative 2 is going to E2. Hey, there's our set. Those are all the numbers that are going to E2. In other words, these are the evens. I kind of picked the letter E here because their difference is even. Well, what numbers are going to E1? Well, 1 is going to E itself. 3 is going to E itself. 3 is going to E1. Those are going to be all E numbers. 5, 7, aha. And going the other direction, negative 1, negative 3, and negative 5. Well, you see these are all the odd numbers. Now at the very beginning, those are all the odd numbers. That's a set of all the odd numbers. We call this congruence mod 2 relation. There's another way that we can write m minus n is even. In fact, there's a couple ways we could write it. We could write that 2 divides m minus n, or we could write that m is congruent to n mod 2. All of those ways are ways of expressing this idea. And the way that's most popular is this mod 2. What if we now take a look at this, instead of mod 2, look at it with mod 3, where we make t, and I'll use t for t, for 3. It's a relation that goes from the integers to the integers, where all the ordered pairs that are in their cross product. Well, m is going to tn means that 3 divides m minus n. If you think about what we saw before, another way of writing this is m is going to be equal to n mod 3. Well, does 3t6? So what I'm asking here, if I do it the first way, if I look at 3 minus 6, well, 3 minus 6 is a negative 3, and that's divisible by 3. So those would be, so that is a yes. Does 3t7? Well, 3 minus 7 is a negative 4. That's not divisible by 3, so that's a no. Does 3t a negative 3? Well, that one's a yes, because if you look at 3 minus a negative 3, that is 6, and that is divisible by 3. Okay, these kind of look a little clear. Things are going to t3 if they're multiples of 3. How about 2? Does 2 t5? If you take 2 and subtract 5, that one does give us something that is divisible by 3. But if you take 2 and subtract 4, we get something that is not. So 2 does not t4. So now I'm going to ask the question, what numbers are going to t0? The numbers that are going to t0 will be 0, 3, 6, 9, 12, negative 3, negative 6, negative 9, and so on. In other words, we're looking at all the multiples of 3. Which ones are going to t1? Well, they're going to have to be one more than that. 1 more than 0 is 1, 1 more than 3 is 4, 1 more than 6 is 7, 1 more than 9 is 10, and so on. Now be careful going the other way. 1 more than negative 3 is negative 2, 1 more than negative 6 is negative 5, 1 more than negative 9 is negative 8. So those are all the numbers that are going to T1. And the numbers that are going to T2 would be 2, 5, 8, 11, and so on. Going the other way, negative 1, negative 4, negative 7. Notice something here, to use some vocabulary from before. When we do congruence mod 3, it partitions the integers into 3 sets. The sets of multiples of 3, multiples of 3 plus 1, multiples of 3 plus 2. Just like when we did congruence mod 2, this partitioned the integers into 2 sets, the evens and the odds, and everything has to be either even or odd. One more kind of funky one here, a relation on a power set. Suppose you have a set with ABC in it. You may remember that the power set is the set of all the subsets of that set. And if I wanted to then look at a relation here that says A is going to SB, it says A, as that set, has more elements than B. So does the set containing A, that's supposed to be a B, A, B, and C, S, B, C. Well, this has more elements than this one, so yes, it does S it. Does the null set S this? No, because it doesn't have more elements. Does this set S this one? Yes, it does. You might look at the beginning of this chapter, which is section 8.1, for some additional examples.